hard. Okay, so two means works very similarly to two proportions. In other words, we have two different populations and we are interested in the difference in the two means from those two different populations. So the difference in mean height between men and women, for example, or the mean number of hours spent studying, comparing freshmen to seniors, whatever it happens to be, you've got two distinct populations. And then we are comparing the mean of some measurement for each one of those populations. So, of course, problem is with populations, they tend to be super large. So we cannot calculate things from a population directly. So instead, we take an estimate from two independent samples. So our estimate, X bar 1 minus X bar 2. So X bar 1 means the mean from sample 1. X bar 2 means the mean from sample 2, and we subtract those. And the distribution of X bar 1 minus X bar 2, sampling distribution, okay? Big surprise, it will be a normal model if your samples are large enough. And the mean of X bar 1 minus X bar 2 will be mu1 minus mu2. In other words, if you have random samples, this will be an unbiased estimate of mu1 minus mu2. So it'll be an unbiased way to estimate what we're trying to estimate, which is mu1 minus mu2, which means that'll be the center of our distribution. Standard deviation. We're subtracting two means here, two distributions. We know that we cannot subtract two random variables when we are trying to find the standard deviation. We cannot subtract standard deviations, but what we can do is add the variance. So here is the standard deviation of my first sample. Sigma divided by the square root of n, remember, is the standard deviation of a sample mean. Square it, because that turns it into variance. We do the same thing for the second sample, sigma 2 divided by the square root of n2. Square it, that's variance. We can add the variances, and then we can take the square root of the whole thing. Okay, cleaning it up. The squaring of the square root can disappear. The squaring of the square root can disappear. So we end up with the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. This is an AP formula. Okay. However, when sigma 1 and sigma 2 are unknown, which they will be, because what are these? These are the standard deviation of a population. It's the typical distance away from the population mean. And we don't know what the population mean is. That's why we're doing this, because we don't know what those values are. So how in the world would we know what the standard deviations are if you have to calculate them by subtracting the population means that we don't know? So what ends up happening is instead of sigma 1 and sigma 2, we use S1 and S2. Those are the standard deviations from the sample. So now we're estimating this. It's now called a standard error because we've estimated it. Doesn't mean we did anything wrong. It just means that there's a little bit of more error involved in here. And now our normal model turns into a T model. So whenever you estimate the standard deviation by substituting in S in place of sigma, you allow a little bit more error involved in our calculation. So our normal model now becomes a T model. Now, T models, we know, have degrees of freedom. How do we find the degrees of freedom when we have two different samples? There are a few options here. Option 1, you can just take the smaller of the two samples and do n minus 1. So just pick the smaller, do n minus 1, and then you can look up T stars and all of that on your table. Just do the normal stuff that we do with T's. Option number 2, here is the formula for calculating the degrees of freedom using two samples. Now, this is not on the formula sheet, so you would need to memorize this. So my suggestion is don't do that. So you do not need to memorize this. Nobody is going to do that. The only person who is going to use this formula for the degrees of freedom is option number 3, doing it on your calculator, and your calculator will do that formula for you, so you do not need to know that formula. Okay, it is very complicated. So I mean, if you look at it, fun to look at, but no, you do not need to memorize that. So how are we going to end up doing degrees of freedom? We are basically going to be doing everything on our calculator because that's what a statistician would do, because it is way easier, because our job as statisticians is not to compute stuff. Calculators and computers do that. We interpret. So what they need people for that computers and calculators cannot do is make sense of what we see after the computations are done. So inference is confidence intervals and tests. So a two-sample t-interval. Step one, define both parameters. So this is our P. So define both of your parameters. Your parameters will be something like mu1 equals mu2 equals. You can use A and B. You can use M and W if it's, you know, men and women, whatever. But just define your variables using the symbol mu, your parameters, not your variables, your parameters. Step two, check your assumptions and conditions. Okay. So just like proportions, because we have two separate samples, we do need to have the two samples be independent from each other. So these conditions should be pretty familiar. Random samples that are independent from each other. 10% condition for both samples. You got to check each sample separately. So sample 1 is less than 10% of its population. Sample 2, N2, is less than or equal to 10% of its population. That's for the independence within the sample. Third thing is your sample needs to be large enough. In order to use the central limit theorem, which allows us to use a normal approximation and then a t-model, is if your sample is large enough. What's large enough? Go back to chapter 22. If n for each sample is 30 or bigger, it's large enough. If n is less than 30, you got to look at a graph and look for symmetry and make sure that there's no outliers. So it's a little bit more complicated when your sample is small, but if your sample is at least 30, then it's super easy. You just say my sample is large enough. So we can use a normal model, which converts to a t-model, because we're going to be using our standard error here instead. So we take the difference in our two sample means, plus or minus t star. You can get that from a table. And then the standard error of x bar 1 minus x bar 2. This is on our formula sheet. So if I go back to our formula sheet, here is the generic formula for a confidence interval. It's your statistic. X bar 1 minus x bar 2 is the statistic in this case, plus or minus the critical value, that's the t star, multiplied by the standard error of the statistic. So on page 2, you can see, when we're doing two populations, our statistic is x bar 1 minus x bar 2. The standard error of said statistic is this, the square root of s1 squared over n1 plus s2 squared over n2. So if you ever had to use the formula to do it by hand, that's where you can find the pieces that you need. Really, the time where you might need that is multiple choice. If they say which one of these formulas is set up correctly, you need to be able to go through and judge that it is set up correctly. But the reality is when you're doing free response, everyone pretty much does this on their calculator. Okay, so step 3, you need to name your interval or provide the formula. The name of the interval is a two-sample t-interval, and say what degrees of freedom you're using. And you need to provide the interval. So I is actually calculate the interval. The interval will end up looking like this when you're done. Will be two values, a comma b. And then the last thing is you need to interpret your interval in context. So something like, I am 95% confident that the interval from A feet to B feet captures the true difference in mean height between women and mean height of men, or whatever it happens to be. So right here is where you would put your context. Okay, so your confidence interval whether we are doing means or proportions, when we have two of them, your confidence interval may have two positive numbers. In other words, this number could be positive and this number could be positive. What does that tell us? Since all the values are positive in our confidence interval, that gives us evidence that the second one here is smaller than this one. When you subtract these two numbers and you get a positive number, it means this one is smaller, that one is bigger. So we can actually make that conclusion if all the numbers in the confidence interval are positive. If all the numbers in the confidence interval are negative, so negative comma negative number, that means that the mu2 is bigger, or the p2 is bigger, because that's how you get negative numbers, subtracting a bigger number from a smaller number. If the left endpoint is negative and the right endpoint of your confidence interval is positive, that means 0 is in the interval, which means there is not enough evidence of being any difference between your two values, between your mu1 and your mu2. So in other words, if 0 is a feasible value on your confidence interval, it is feasible that the difference is 0. In other words, it's possible that there's no difference. So there's not enough evidence of a difference. Sometimes they ask you that when you have a confidence interval based off of two means or two proportions. They'll say, based off of your confidence interval, do you believe that there is a difference in the two means? And if 0 is in your confidence interval, you say no. Because 0 is in my confidence interval, there is not evidence of there being a difference. If both endpoints of your confidence interval are positive, then you can say, yeah, since my entire confidence interval is positive, there is evidence of a positive difference, meaning that the first value here is bigger than the second one. Okay, to do a test, step 1, define both of your parameters. Again, mu1 and mu2. Okay. Set up hypotheses. These are almost identical to proportions, except their means. So instead of P1, P2, it's mu1, mu2. But our null is always going to be 0 difference. You can write it like this. Some people like to write it like this. It's the same thing mathematically. Mu1 minus mu2 equals 0 is mathematically the same thing as mu1 equals mu2. And then your alternative, choose one. Based on the problem, are we doing a greater than test, a less than test, or just a straight out not equals to test? Are we testing for a positive difference, a negative difference, or just a difference? Okay, conditions, same as the two sample t interval, which makes things easy. So next you check your assumptions and conditions. Next, you name the test or provide the formula here for the t statistic. Notice that, oops, there are no bars on my x's here. These are x bars. So you take your two x bars, subtract them. That's your statistic. Subtract 0, because that's what our null hypothesis mean is, 0. Difference in means is 0. Divided by the standard error of the difference. That's how we find our t statistic. It's kind of like a z-score. We call it t because we're using a t model. Okay. So next thing after naming your interval is you got to provide your test statistic and your p-value. Next, you got to observe, is your p-value less than the significance level? So make an observation about the size of the p-value. Make a decision. And state your conclusion in context. Same as other tests. If my p-value is less than 5%, I reject the null. There is convincing evidence that whatever the problem is asking. Okay, so all of that is the same as what we've been doing. So let's just do an example. Calculator skills, there is a test on 0. It's called two sample t-test. Interval is 0. There is a two sample t interval and there is a two sample t-test. Choice 4 versus choice 0 on a calculator, assuming you have a TI-84 or similar. There's the two sample t-test, choice 4. Scrolling down, you will see the 2 sample T interval. And this is where I did intend to say we never pool on means. And I'll talk about what pooling means when we go through and do this as an example. Okay, resting pulse rates for smokers and non-smokers. 2 simple random samples are taken. First random sample is 26 smokers. They had a mean pulse rate of 80 beats per minute and a standard deviation of 5 beats per minute. 32 non-smokers, random sample was taken. They had a mean pulse rate of 74 beats per minute and a standard deviation of 6 beats per minute. Okay? Histograms of both samples were roughly symmetric. Is this evidence that smokers have higher resting pulse rates? Lower pulse rates is better than a higher resting pulse rate because it is that your heart is not working as hard. If you have a very high resting pulse rate, then your heart is working a lot harder than someone who has a lower resting pulse rate. So people that are very active and athletic tend to have lower pulse rates because they have, honed their body into a more efficient machine. So let's take a look at what we got here. We have 2 random samples. So we've got smokers and we've got non-smokers. So we are interested in the mean overall, the average resting heart rate for smokers versus non-smokers. So the first thing that we need to do is define our 2 parameters. So mu, you can call it mu1 and mu2. You can call it mu sub s for smokers and mu sub ns for non-smokers. It is completely up to you. I'll just do mu sub s, which is the mean resting pulse rate of smokers. Okay, and that is all smokers. So that's the mean pulse rate for all smokers, which we obviously cannot calculate because there's no way we can take a calculation from all smokers. So mu sub ns, or n if you want. Now let's just do n. Doesn't matter. That's why we have to define it. So whoever's reading this knows what your symbols represent. So mu sub n is going to be the mean resting pulse rate of non-smokers. Now we're looking for evidence. So that means this is a test. When it asks you if there is evidence of something, you got to test for evidence, which means we need a null hypothesis. The null hypothesis, when we have 2 separate independent samples, these are independent because one group is smokers, one group is non-smokers. They are completely separate populations and they're completely separate samples. So our null hypothesis is going to be that the difference is 0 or that one is equal to the other. So it's your choice of how to write that. So you could write that the resting pulse rate of smokers is equal to the resting pulse rate of non-smokers. So you can write it like that. If you don't want to write it like that, you can say subtract them and say you get 0. That's the same thing. Your choice. One advantage to doing it this way has to do with the alternative. Because here's my smokers, here's my non-smokers. Smokers, non-smokers. What are we testing for? We are testing, do smokers have a higher resting pulse rate? So we are testing of whether that is greater than that. The smokers have a higher resting pulse rate than the non-smokers. So we are testing if there's evidence that the mean for the smokers is larger than the mean for the non-smokers. Right? So those are our 2 hypotheses. The null is that they're exactly the same. So in other words, there's no difference in pulse rate whether you smoke or don't smoke. And then the alternative is that smokers have a higher resting pulse rate than non-smokers. Okay. Some other information here, just to write stuff down, is our sample sizes. 26 is the sample of smokers. So on the side here, I'm just going to say my sample of smokers is 26. They had a pulse rate of 80. So that is my X bar for smokers. And they had a standard deviation, whoops, not that one. They had a standard deviation of 5. Now this is all from my sample. So my smokers, there were 26 of them in my sample. They had a mean of 80 beats per minute with a standard deviation of 5. And then I have my non-smokers. There were 32 of them. And they had a mean of 74 with a standard deviation of 6. Okay, so I'm just writing that on the side so that I've got everything I need for the problem. So it's just a good idea when you got all these numbers in the problem, make sure you know what they all are. So this is basically all the given information and how I would label it based off of how I chose S for smokers and N for non-smokers. Okay, next up, we got to check our conditions. Okay, we have 2 samples. What do they have to be? They have to be random. What else do they have to be? Yeah, independent of each other. Do you think that that's the case here? Right there. 2 simple random samples, so they are random. And if they are random, I think it's safe to assume that they are independent of each other. In other words, the pulse rates of these 26 smokers should have nothing to do with the pulse rates of these 32 non-smokers. So if they are random, that should be the case. Of course, if they're related somehow, then their pulse rates might be affected based off of, genetics or something, or if they all live in the same area or something like that. But based on how they said that they found them, we have to assume that they are independent. So randomization. So both samples are simple or random samples and should be independent. Okay. Now we are sampling without replacement. In other words, we're not taking the pulse rate of the same person more than once. These are 26 separate people. So we do need to check our 10% condition. So my first sample, 26, is less than 10% of all smokers. I don't know how many smokers there are in the world, but I am pretty confident that it is greater than 260. And likewise, 32 is less than 10% of all non-smokers. You do have to write that all out. You can't just say 10% condition, check. You got to actually write down what you checked. Okay, last thing is we need a sample that is large enough. Now that sample is large enough because it's greater than 30. That one is not. However, is there anything in the problem that tells us it's going to be okay? Yeah, Catherine? Yeah, right there. They told us, they graphed it for us. So we don't have to graph it. We don't have the data, so we can't anyway. But they graphed us for us and they got histograms for both samples that were roughly symmetric. So even though the 26 is a little smaller than we like, that gives us evidence that it's okay to proceed. Okay, so large sample. So we have our first group is 26, which is less than 30, but histogram is symmetric. So even though our sample is less than 30, the histogram is symmetric, so it's okay. For the other group, it's 32, which is greater than or equal to 30. So we are good. If it wasn't, histogram is symmetric for that one too, but it is greater than or equal to 30 regardless. So conditions are met for a 2 sample t-test. So we are going to do a 2 sample t-test. So stat test 2 sample t-test is choice number 4 on here. So you find the 2 sample t-test. And again, just like Friday, you have 2 choices. Do you have the data in a list? If so, it'll ask you which 2 lists. If you don't, then you got to go over to stats and enter all of this, which we do have. We do have our X bar, S, and N for each sample. So group 1 is my smokers, because that's the one I'm listing first right here. This is group 1, so it's my smokers. So I had a sample mean of 80, sample standard deviation of 5, and a sample size of 26. My non-smokers, I had 32. Oops, I had 74 as the mean. Standard deviation is 6, sample size is 32. And then it asks you, what did you use for your alternative? And look at my alternative is a greater than test. So right there, greater than. It will ask me if I want to pool. Do we want to pool? No. What they are asking is, do we assume that the standard deviations for both groups are actually equal? That's what pooling does. It's assuming that the 2 standard deviations for both groups are equal. We really have no way of knowing that. There's no reason that we would need to assume that. So we are never going to pool. So there's no reason why we're not making any assumptions here about the standard deviations for both groups being equal. So we will always just say no. Hit calculate. There's my t-statistic. There's my p-value. Notice this over here. Look at my degrees of freedom was 55.95. They got that by using that really ugly highlighted formula. So we don't do it. Calculator does it for us. And then it just also spits back all the information that we already entered in here. Okay, so what do we need to write down? We have our degrees of freedom equal to 55.95. My t-statistic was 4.153. And my p-value is in scientific notation. It's 0.00006. Scientific notation means I take that decimal right there and I move it 5 places over to the right. So you move it once and then you got to add 4 more zeros in order to move it 5 places to the right. So in other words, the 5, which I rounded up to 6, is the 5th number after the decimal. Now, if you don't want to write it like that, you can write it in scientific notation, or you could even say is close to 0, because that's obviously very close to 0. So you could say your p-value is approximately 0. Important thing is, this is less than any significance level, assuming 5% significance, because that's what we use, unless we are told otherwise. That is definitely way less than 0.05. So we can make our conclusion. So since the p-value of 0.00006 is less than or equal to 0.05. I reject the null hypothesis. And now I got to say, well, what does that mean about smokers and non-smokers? When we reject the null hypothesis, we have found evidence. In fact, this is very strong evidence. Our p-value is super low. So we have convincing evidence that smokers have higher resting pulse rates than non-smokers. So we have convincing, or you could say strong evidence, very strong evidence in this case, that smokers have higher resting pulse rates. Okay, that is logical. I mean, if we believe smoking is not good for your health, this would be one of the ways that we would measure that, is having a higher resting pulse rate than non-smokers is one of the ways that smoking is not good for you. It's making your heart work harder. Okay, this last section here is looking at two different math curriculums. So the Core Plus Mathematics project, the CPMP, is an innovative approach to teaching mathematics that engages students in group investigations and mathematical modeling. Kind of sounds similar to CPM, if you guys remember back that far. And you guys did the CPM curriculum in integrated 1, 2, and 3, and in middle school for that matter. After field tests in 36 high schools over a 3-year period, researchers compared this curriculum versus using a traditional curriculum. In one test, students had to solve applied algebra problems using calculators. Scores for 320 CPMP students were compared to those of a control group of 273 students that were using a traditional math program. Computer software was used to create a confidence interval for the difference in the mean scores. And here is our confidence interval. It was a 95% confidence level. And here is the interval. So here's the interval right here. And they were comparing the mean MU for mean mu, the mean of the CPMP minus the mean of the control. The control was the traditional group. So part A, what was the difference in sample means? So it's asking, what was the difference in the two sample means? That's all right, control. That's what they're asking for. So this is our estimate. Where is this located in the interval? It's exactly in the middle. So this is asking basically what was the point estimate? We're trying to estimate the difference in these two means. So the difference in the means and the samples would be our point estimate. So best way to calculate that would be to take the two endpoints of your interval, add them, and divide by 2. That's how you find a midpoint. To find something exactly in the middle between two numbers, you add and divide by 2. Also known in this class as the average. Okay, so the samples saw an 8.5 point difference in the mean scores. And then it says, what's the margin of error? And I didn't leave myself enough room here, so I will put the 8.5 over here. And then I will find the margin of error. Margin of error is half the distance of the interval. So the margin of error is the distance from the center, from 8.5 to either endpoint. So I could just take an endpoint and subtract 8.5, or I could find the distance between these and divide by 2. So whichever way you want to do that, I'll just take 11.427 and subtract the 8.5. 8.5 is in the center, so the margin of error is the distance from the endpoint to the center. And that's a margin of error of 2.927. Okay, so you make sure you can find a point estimate in the middle of a confidence interval and figure out a margin of error. Okay, if we had done 98% confidence interval instead, would the margin of error be larger or smaller? This was a 95%. What happens when you increase your confidence? What happens to your margin of error? It becomes larger. That's the trade-off. I'm more confident now, but I have a larger margin of error. So increasing confidence to 98% will increase the margin of error. So that's why we don't always make 99.9% confidence intervals. It'd be nice to be that confident, but we end up with a larger margin of error. So that's kind of why 95 is the most common, just because we've kind of settled on that's a good balance between the two. Okay, C, explain what the calculated interval means in this context. So interpret the confidence level. So let's take a look at our confidence interval. What does that tell us? 95%. So we are, that's not are 95% confident that the interval from, what was it, 5.375? Did I write that right? Nope, 5.573. Got my numbers backwards. And 11.427 captures the true difference in mean scores between students that use the CPMP curriculum and traditional curriculum. Okay. Notice that both of the values in my confidence interval are positive. So I could also say that's evidence that the CPMP curriculum has a higher mean score, anywhere between 5.5 points higher to 11.4 points higher. That's what we believe. So we do not believe, based on that confidence interval, that there is no difference. We believe that there is a difference, that the CPMP curriculum has a higher mean score than the other. But interpret the confidence level. Why are we 95% confident? Okay, if we created many two sample T intervals like this one, I expect about 95% of them to capture the true and difference in mean score. Okay, that's why we're 95% confident. We grabbed two samples and created a 2-sample t-interval from our 2 samples, but if we repeated this process many times, we expect 95% of these confidence intervals to capture the true difference in the mean scores between the 2 programs. So did ours? I don't know, but we're 95% confident that it did, okay? Does this result suggest that students who learn with CPMP will have a significantly higher mean scores in algebra than those in traditional programs? So what do we think? Yeah, because all those values are positive. Okay. Since all the values in the confidence interval are positive, we have convincing evidence, at the, I'm going to fill that in, level of significance that CPMP students have significantly higher mean scores in algebra. Okay, now significance level. Okay. This was based off of a 95% confidence interval. A 95% confidence interval means that we created a normal model. I realize it's really a T model, but it works the same way, with 95% in the center. A confidence interval is always the percent in the center because of the plus or minus thing. You've got your estimate and you go plus or minus on either side. Now we are testing for a higher mean score, which means my significance level is the higher tail. If we were just testing for a difference, we would add the 2 tails together. If we were testing for a lower mean, we would just look at the bottom tail, but we're looking for a higher mean score. So this right here is my alpha level. What area is there? Okay, 95% in the center. How much is left? 5%. And since there's 2 tails, we got to cut it in half. That means my alpha is 0.025. So this is the 2.5% level of significance. So when you do a confidence interval to judge whether there is evidence, you are allowed to do that, but you do need to say what significance level you are using. So anytime you want to do a confidence interval instead of a test, still need to write the hypotheses and everything, but you are allowed to do that, but you will not get full credit if you do not name the significance level you used. So if you do choose to do that, you run the risk of not including the significance level in there. Okay, last one. During the study, students in both programs took another algebra test that did not allow them to use calculators. So on that last page, it was a calculator test. So here is some information from 2 different samples taking a test without calculators. Are the mean scores significantly higher for the CMPM students? So here's the mean for the CMPM. Here's the traditional. We want to test whether the CMPM students scored significantly higher. So hypotheses. What's the null? Should define my parameters. I didn't leave enough space to do that. So let's let this be CM, CPM. Mean score for CPMP students. And this would be all students that ever could be taught using CPMP. I don't know why I have trouble saying that. And this would be the mean score for traditional students. Okay. Null is always that the difference is what? 0. There's no difference. So you can use 1 minus the other equals 0, or you could do they're equal to each other. Okay, and then the alternative. Okay, we're looking to see whether the CPMP students score higher. So the mean for the CPMP, are they higher than the mean for the traditional students? So something like that. Tell me what symbols you're using, and then use those symbols to create your null and alternative hypotheses. If you don't want to write equals like this, you can do this minus this equals 0. It's the same thing. Okay. Okay, assumptions for inference are satisfied. Do we think that they are satisfied? Let's do this verbally because we're running short on time. We got 15 minutes, but are they satisfied? So randomization. So do we think these are random samples? Doesn't specify here, but it did talk about up here. Nope, it never did. These were field tests in 36 different high schools over a 3-year period. So that would be the one condition that we are not absolutely sure is satisfied. So in other words, we should be careful extending our conclusions here to any high schools that are different than the 36 that were chosen. So they chose 36 high schools over a 3-year period to run this field test. We really should not be making conclusions outside of those types of high schools. I don't know if there's anything special about those types of high schools. Are they urban schools? Are they rural schools? Are they schools, that have different demographics than other schools, different socioeconomic levels than other schools? I don't know. But they are not completely a random sample, so we just need to be careful of that. So I would say for randomization, they weren't necessarily chosen randomly, but if we treat it as a random sample, just, we need to be careful that we don't take this inference and apply it to schools that are different. 10% condition should be satisfied. So our sample size is right there, is N equals 312 and 265. That should be less than 10% of all the students who could theoretically be taught using either of those two programs. And both samples are clearly large enough. Okay, so I'm just going to say we discussed. I don't want to write that all out. Okay, here is the printout from a computer. We don't even have to put it into our calculator. They did it for us. So here is our t statistic. Here is our p-value. They did a 2-sample t-test on a greater than hypothesis, which is what we were doing. So explain what our p-value means in this context. So what does this mean? We were testing whether the difference was 0. So this graph is the sampling distribution. So this is the sampling distribution of X bar 1 minus X bar 2. X bar 1 is the CPMP students and X bar 2 is the traditional. Okay. If we take a look here, we had a difference of, what is that, 1.6? If I subtract those two, there's a difference of 1.6. So we had a difference of 1.6. The p-value, since it's a greater than test, is that area. So it's the probability of two samples showing a difference of 1.6 points in their mean scores or higher if the null, which is that there is no difference, is actually true. That's what the p-value is. It's a conditional probability. So it is the probability. So I will say this. There is a 0.1363 probability of two samples showing a difference in mean scores of 1.6 points or more if, in fact, there is no true difference in mean scores between CPMP and traditional. Okay. So if there's no difference, if the two programs are identical, specifically when they're testing without a calculator, I should say, without a calculator. Without a calculator. Calculator. So if students are taking a test without a calculator, if the two programs are identical, the chances of seeing what we just saw, a 1.6 point difference, is about 14%. Is that unusual? Is 14% something we consider unusual? Yeah, not really. So random chance, 14% chance that this difference would occur just by, you know, randomization, just by normal random chance. So it's not surprising. So we have no reason to doubt that this is true. In other words, we cannot reject the null. This p-value is not small. It's not surprising. It's almost 14%. It's not less than 5%. So since the p-value, which is 0.1363, is greater than or equal to 5%, I fail to reject the null hypothesis. And if you fail to reject that null hypothesis, we are saying we do not have convincing evidence of anything. So right here, are the mean scores of the CPMP students significantly higher? We don't have evidence of that. Okay. There is not evidence to suggest mean scores students are significantly higher. And of course, this is when testing without a calculator. Because on the other page, we actually did see a significant difference here on the other page. Because of the fact that all the values in our confidence interval were positive, we did see a significant difference in scores when the students were allowed to use a calculator. But over here, when the calculator was taken away, we did not see a significant difference between the two programs. So is CPMP better than traditional? Kind of hard to say. First off, we have those 36 whatever schools that were chosen. We don't know if they are representative of all high schools. So we can only generalize to schools that are like those, but it appears that if you test students with a calculator, we do see a significant difference, but if we test them without one, we don't see a significant difference. So I would assume that the CPMP program, I have trouble saying that every single time, uses a calculator pretty regularly. So the students are becoming much more proficient in solving problems with a calculator, but where they lack is in the ability to solve problems without a calculator because they really don't do any better than the traditional. So that would kind of be the overall conclusion here. Okay. So if you were an educator and we're looking at these two different curriculums, that's kind of what we would see. Okay. And again, caveat is they only tested these particular schools, so we can only generalize towards schools that are similar to these. Okay, so that actually takes us right to the end of class. So we don't really have a lot of time for you guys to work. But your assignment is the chapter 23 book assignment on MyMathLab. Should be open. I apologize that the other one closed early. So I did fix that yesterday, but the one for today should be open. And then also read chapter 24. Chapter 24 is, again, two means when your two samples and populations are paired. So when you're looking at samples that are not independent. This was all two independent samples. Chapter 24 is the end of means. So after chapter 24, we're done with means. But it's like, what do we do when your two samples are paired and not independent? Okay, so that's where we leave it off. Okay, so any questions? So like I said before, we will finish off means tomorrow, and then we will start the last two chapters in our book at the end of this week, right before we go to Thanksgiving break. We'll finish up the last chapter when we get back from Thanksgiving, and then we'll be able to have our last unit test first week of December, and then that'll give us 2 weeks of AP review. So in other words, we've got 3 chapters to go. Chapter 24 to finish off means, and then just last 2 chapters. And that's it. We are so close to being done with AP Stats. Okay. So I'm going to stop my recording.